This was the matrix representation we got for the fully implicit method for the diffusion equation. And remember that, we're going to put here again on the left everything which depends on j plus 1, j plus 1, j plus 1. And everything which depends on j, we're going to put it on the right hand side of this equation of the matrix representation. And our aim was actually to convert that matrix, which is not square, in another representation involving a square matrix. In this case, that we're going to call it M, evaluated at time j plus 1, which is going to multiply this E vector evaluated at time j plus 1, plus some another vector evaluated at time j plus 1, which is going to be equal to this vector. So we need to transform basically that matrix here in a square matrix. And we're going to do that. The aim was to do that using the boundary conditions. And of course, it's going to depend on the kind of boundary conditions that we're going to consider. So first here, we are going to consider here the Dirichlet boundary conditions. So what does it mean? It means basically that that we do know which are the values of the u function, both on the left hand side, on the left border, and the right border. Therefore, at any time. So that's the thing of the boundary conditions. We do know what's the value of the u function evaluated in the index corresponding to the space 0 and the index corresponding to the space nx at any j. So what does it mean? It means actually that in this column vector that we have to use in order to evaluate the u function at the next time step, these two ones, this one and this one, they are not unknowns because of the boundary conditions, of the Dirichlet boundary conditions. They are knowns already. So we can discard this one somehow. Of course, they are going to have some effect in order to calculate the others, but we are going to do the following. We are going to take basically a square matrix from here, this one. So we are going to eliminate this column here and the last column here, because this column here is multiplying this component here, and this component is not unknown. It's basically it's a constant, it's a number, and the same one as this one, which multiplying this one, which again is not unknown. So we are going to center in a vector which corresponds to the unknown component of the u function. So these are the unknown components of the u functions. And the matrix which is multiplying the unknown components of the u functions is this square matrix, because this is actually a square matrix. So the one we do have here has the dimensions of this one are nx minus 1 times nx minus 1. This is actually a square matrix. So this square matrix is going to multiply this one, but besides that, we do also have to include the component or the effect of minus alpha, which is multiplying this component here, and that will add some value to this to the value of u evaluated at the point 1. And the same with this one, with the minus alpha, that's multiplying this one. And we are going to do that, adding just another column, which will correspond to this arc vector here, with this basically these two components, with this one and this one, with the product of this one with this one, and the product of this one to this one, that they are not included when you are multiplying this square matrix with these unknown components of the u functions evaluated at j plus 1. So this is basically the strategy that we are going to follow. And using that strategy, this is the representation that we do have. That will be the matrix representation that we do have for the fully implicit method with the Dirichlet boundary conditions. as this is the square matrix, which is multiplying the unknown components of the u function evaluated at time j plus 1. And besides that, we do have to include also these two other contributions, which were missing, of course, when we are just considering this square matrix, but they are actually when we are considering the full matrix elements. But the interesting part of that is that these two ones, they are not unknown. They are just, let's say, two known functions, or just even numbers, depending if they change with time or not. So when we are writing in this way, basically we actually got our aim, where basically means that here on the left we do have a square matrix here, the square matrix, which in principle it's evaluated at time j plus 1. Here I'm writing the subscript here L, which basically saying that this is a matrix here that we are writing on the left. It's multiplying this u vector. This u vector will have just nx minus 1 components, which are the unknown components of the u vector, plus this r, which is a vector. This is the vector which includes, as you can see here, the two boundary conditions in the Dirichlet, boundary conditions. So these two are known values, which is equal to the u vector, which has, again, nx minus 1. So we already got it, and now, as we do have a square matrix here, we can clear, because the basic aim we do have here is to clear an explicit expression for this vector here, for the u vector evaluated at time j plus 1. And now we can do that because we have this A matrix, which is a square matrix. So how to get that? That's pretty easy. Basically, what you have to do is just bring that R vector to the other side, which is basically is unknown. That's what we have. And this one will go to the other side again, just using the inversion. We have to use to multiply this one, the one we do have here, by the inverse of this A matrix we have explained before. We have just defined before, evaluated at time j plus 1. And doing that, now you can see that we already got our aim, which basically was to clear an expression for the u function evaluated at time j plus 1, just knowing which are the value of the u functions at time j. And this is the expression that we can use in order to go step by step in order to get all the values of the u functions in our time and spatial mesh.